Alright, this video we're going to talk about Unit 3, Objective 1.3, the definite integral. And what a definite integral is the way to find the total area under a curve between 2 points. So we've seen it with geometry, we've seen estimating the area under a curve with Riemann sums and trapezoids. But today we're going to talk about the fundamental theorem of calculus, and that's going to allow us to find the area under a curve algebraically. So what the fundamental theorem of calculus says is if capital F prime of x equals lowercase f of x, then the integral from a to b of lowercase f of x with respect to x is equal to capital F of b minus capital F of a. So what this means, because that probably doesn't mean a whole lot to you right now, but what this means is right here, capital F prime equals f of x. All that means to us is they're letting us know that capital F of x is the antiderivative of lowercase f of x. So what we saw in the last video allowed us to find this capital F of x, the antiderivative of lowercase f of x. So how we're going to use that is this integral from a to b. We find the antiderivative, we plug in b, we plug in a, we subtract, and that's going to give us our total area under the curve. It's going to give us the definite integral. So what we need to think about as far as this blue box here is the integral tells us the total change in the antiderivative of a function. Now we've talked about that phrase when we did Riemann sums and trapezoidal rules. That's how we're going to explain the meaning of an integral. But now we can actually see where it comes from. It comes from the fundamental theorem of calculus. So we always want to go back to the integral being the total change in the antiderivative. That phrase is going to be very, very important for your justifications on your free response questions. Yes, the integral tells us the area under the curve, but that's not what it means. It means the total change in the antiderivative. So all we really have to do is use the rules that we had in the last objective, the last video, and plug in the upper limit, plug in the lower limit, subtract, and that's all we need to do to find our integral. So if we think the integral from 1 to 8 of, let's just go something easy, let's say 4x to the third plus x minus 4 with respect to x. So we know that the capital F of x, the antiderivative based on our rules, if we increase to 4, divide by 4, increase this to 2, divide by 2, increase this to 1, divide by 1, and then we have that plus c that we needed on there for our antiderivative. We're going to see that when we're finding the integral, this plus c we're not actually going to need to use anymore, and you'll see why here in a second. But if all of that there, we can simplify a little bit and say 4 over 4 is just 1, so x to the fourth plus 1/2 x squared minus 4x plus c. So all we need to do with what we have is take our antiderivative evaluated at 8 minus our antiderivative evaluated at 1. So if we go back to what's up there in the blue box, the total change in the antiderivative, f of b minus f of a and b are 1 and 8. So f of 8 is going to be 4096 plus c minus, and if we put f of 1 in parentheses, we're going to get negative 2.5 plus c. So there's our fundamental theorem of calculus. We do need to simplify it a little bit. Distributing our negative, 4096 minus negative 2.5, so plus 2.5 is 4098.5. And then you'll notice that we have the c minus c, so that's going to give us a 0. So 4098.5 is the total area under the curve of 4x cubed plus x minus 4 from 1 to 8. Now you'll notice every single time you take an antiderivative, you have this plus c, which means when you do f of b, you're going to have a plus c. And when you do f of a, you're going to have minus a plus c. And those are going to cancel out 100% of the time. So if we're finding a definite integral, we don't actually have to put our plus c when we find capital F. Now a little bit of notation and then we will call it quits on this video. A lot of books, a lot of places will say x to the fourth plus 1/2 x squared minus 4x. And then you'll see this little line right here that and a 1 and an 8. This just means plug in your 8, subtract the value from when you plug in your 1. So this little bit of notation with that bar and a 1 and an 8 tells you to do this stuff down here. We are going to focus a lot in this class writing it this way, because when we do accumulation functions, writing it that way is going to be a little bit more useful. So that'll do it for this video. We'll see you in the next one.